Hello, everyone. This is Dr. Andrew Chrysler teaching EE 4495 Senior Seminar at Idaho State University. In this lecture, we will be continuing our discussion of system-level design, and we'll be doing this by looking at a few examples of how to formulate block diagrams, the process that you use to make block diagrams, and overall just seeing examples of how system-level design works. So let's begin. So first, let's take a very basic design example. Let's say that you're building an electro spray power supply. And so you have gotten some requirement specifications. So you've gone through your needs analysis, you've worked with your customer, you did the needs analysis, you figured out what the problem is and how you're going to solve the problem. And so out of that, you've come up with some requirement specifications. And we will simplify them here a bit, but let's just say these are the numbers that you have agreed on with the customer. You have an input power, output amperage, and some waveform characteristics, including duty cycle, pulse frequency, and amplitude. So based on these specifications, right, you might break down everything into a block diagram that looks like this, where you have your input power, right? And the arrow then points to the input power, goes to the power supply for this, right? So you're working on this power supply, electro spray power supply. It goes into the power supply, and that power supply then gives information to waveform generator, output voltage converter. And you also, in addition to your input power, you have some user control input that describes, what kind of modulation form you want. So you have some controls that go in, and the controls, right, also point to this output voltage converter and the waveform generator. Now, as we discussed in the previous video, right, we have not replicated the waveform generator block or the output voltage block. Right, we have we have an output voltage converter block that does one job. Even though it's used, since it's used multiple times, we instead draw multiple arrows to it rather than having this block appear 2 times. And same with this waveform generator. And then you come up with a power output stage that gives the output waveform. And then each one of these, right, is labeled with what is going between these two. Okay, so from the power supply has a low voltage DC power and a high voltage DC power. And so the line is labeled with that information. That's the arrow is described what is actually occurring in that arrow. And so likewise, the rest of these are also labeled voltage control level. So some kind of signal, waveform controls. This one's a voltage. All right. So each one of these lines is described. So then let's take a look at a second example design, and this one's a little bit more detailed. So let's say that a power utility company, they've determined that they need to measure the quality of their 60 hertz, 120 volt AC supply in residential houses. Okay, so they need to monitor this, determine the quality, and find out what the variation in supply is over time. And that variation they call the flicker. So the power utility, they're looking into the flicker because this is an important measure of the quality. All right, and so the power utility company requests designs for a flicker analyzer so that they can monitor that variation. So first, we might have a general requirement specification. So again, this example is a little unique, but let's say they're their own customer and they know what they want. And so they've put out this, they've been able to develop the requirement specifications for what they want. So these describe what their flicker analyzer needs to do. Their flicker analyzer must have an accuracy of 0.01 volts in order on detecting this. And so this is the flicker. If you have the full voltage with the sine wave, this extra voltage, that would be the flicker. So they need to be able to accurately measure the flicker within 0.01 VRMS, and the flicker analyzer tool must also be able to display the magnitude spectrum of the overall voltage on a frequency from 0.1 hertz to 25 hertz. The utility company also knows that the flicker is bounded, so they know that the flicker actually never gets larger or smaller than 2 volts. They also know that the RMS voltage never exceeds 0.9 volts, and they also know that the flicker does not have any frequency components over 25 hertz. So we will know that we have come up with a solution once we describe a solution, right? We will know that we're done working on our solution once we know that we have a system that can perform this measurement with this accuracy and also display the spectrum over these frequencies. So we need to come up with a system that does this. And these are 2 other important notes, or 3 other important notes that we have about the system. So going back to the system design process, right, what we just looked at, these are some requirement specifications, some numbers that we came up with saying what needs to be done. So we know what we want to do, we know the level of accuracy, and we know what we want to display, but we haven't figured out yet how we're going to do it. So we need to develop some concepts. We need to analyze those concepts. We'll synthesize the solution, and we'll refine as necessary, all along the way, rejecting any unworkable concepts so that we can, in the end, arrive at a good block diagram that describes a system that meets these requirement specifications. So first, in this conceptualization stage, let's take a look at this problem and just think about it some more. And so if you're an engineer on this team, you might ask yourself, well, should we do this using analog or digital methods? And you might determine, right, okay, this is probably going to be easier for us to do in the digital domain. It'll be easier for us to analyze all these signals. Then you might also say, well, we know, right, we have this requirement specification. We must display the magnitude spectrum over that frequency. Well, how are we going to display it? So, you know, there's monitors, you could get an integrated LCD panel, you could do laptops. Well, you might think to yourself too, okay, yeah, laptops, those can also do digital signal processing. And so based on this conceptual stage, you could conceive of a concept that basically takes your voltage as an input, has an analog digital converter, and uses the laptop computer to display your frequency spectrum. All right, so we've completed a conceptualization of the design. We've determined a way that we could do this. And we also made this kind of basic block diagram. It's not very detailed, but it's a start that gives us an idea of what the solution looks like. And then during this step, right, we have rejected ideas that we did not think are good. So we rejected using the analog concept, and we also rejected using a standalone LCD panel. So instead, we decided to go forward with the digital and the laptop. And that's right because laptops could also do the signal processing. All right, so in the synthesis stage, we would look at building a block diagram and finding the function and specifications for each block diagram. So looking at this in more detail, let's come up with a basic block diagram for this, where we have the voltage at the home. We'll make a voltage divider, an anti-aliasing filter. Have an analog digital converter, and get this information sent out to the port of the serial port of the PC. So this block diagram, right, this might be included over here. And so looking at this, we have now synthesized a block diagram that is a bit more complete and each block has functions and specs and describes what the arrows or the linkage between subcomponents are. Now, you don't need to worry about the math, but let's just say that you had gone through all of this. You knew the specs of every different part that you had available, and you were really working on this project. And so you could start from the principles that you've learned in all of your classes, and you could do a mathematical analysis of this system. And you could determine using this math, right, that, okay, well, actually, use the components that we're starting with. It looks like we might not actually be able to keep the error between the desired limits to yield the resolution that was required. So if you started with this equation, did a bunch of math, knew what components you had available, all right, all this, after all of that, you realized, well, shoot, what we were planning on doing, what this block diagram was planning on doing, says, okay, we can't actually build this so that it meets this requirement specification of 0.01 VRMS. So that means, right, maybe we should reject the 8-bit analog digital converter, and we should go back and decide instead, well, let's use a 16-bit analog digital converter instead. And by increasing this resolution, all right, we can actually arrive at a final system design that does meet these requirement specifications, right? So we had these two specifications that must be met, right? We know that the project is done when we build something that meets both of these. And so by going through this step, developing the concepts, analyzing and synthesizing them, iterating through this as necessary, you can arrive at this final block diagram where you have a system that you in the block diagram you confidently believe will meet those specs. And you know that it will meet those specs because you were able to break down each subcomponent of the system, analyze the subcomponent as a member of the whole, and determine that yes, the output will be sufficient. So I hope that helps you understand some examples of forming block diagrams, and I will see you in the next class or video. Bye.